Hello, my name is Hyeongju. Today we're gonna study AP Physics 1, equations of motion in two dimensions. We have already learned about kinematic equations for one-dimensional motion. However, real-life situations are rarely restricted to one dimension. This lesson will explore how to apply the kinematic equations to motion in two dimensions. Applying the equations of motion to each new dimension is relatively straightforward. We have already applied this method in our previous lessons. We first studied horizontal motion and then modified our kinematic equations for the vertical to serve freeform problems. However, adapting the kinematic equation to each dimension is only one part of the equation. The other part, which we have not yet covered, is how to relate the equations from one dimension to another. In a one-dimensional world, only need to know how far to go to reach your destination. However, in two dimensions, knowing the distance is not enough. You also need to know which direction to take, for example, north, south, east, or west. To describe motion in two dimensions, we use vectors. In two dimensions, motion can be broken down into x and y component. Where x and y represent the horizontal and vertical directions, respectively. Displacement in two dimensions can be described by the vector r, which has components r sub x and r sub y. The magnitude of the displacement vector is the scalar length, which can be found using the Pythagorean theorem. Velocity and acceleration in two dimensions can also be written as vectors and can be broken down into x and y components. For the velocity vector v at angle theta, the adjacent components v sub x is equals to v cosine theta, and the opposite component v sub y is equals v sine theta. The vector sum of the components v squared equals v sub x squared plus v sub y squared, and tangent theta equals v sub y divided by, tangent theta is equal v sub y divided by v sub x. Likewise, for an acceleration vector at an angle theta, the adjacent component a sub x is equals a cosine theta, and the opposite component a sub y equals a sine theta. The vector sum of the components a squared equals a sub x squared plus a sub y squared, and tangent theta equals a sub y divided by x sub x, a sub x. To solve two-dimensional problems using kinematic equations, we modified them for each specific dimension. The long kinematic equation for the x dimension becomes x equals x initial plus v initial x times t plus 1/2 a sub x t squared. The short kinematic equation for the x dimension is v sub x is equals v initial x plus a sub x times t. The combined kinematic equation for the x dimension is v sub x squared equals v initial x squared plus 2a sub x times delta x. Similar changes can be made for the y dimensions set of kinematic equations. Note that x and y dimension kinematic equation share a common variable, time. To summarize, in this lesson, we learned how to apply the kinematic equation to motion in two dimensions. You can review this video as many times as you want for better understanding. Thank you for watching.